let's discuss collision theory. So we know that in order for a reaction to take place, the reactants, be it atoms, molecules, or ions, they must collide in order to react with each other, right? They must actually come into contact and collide in order to react with each other to form products. Now, the rate of the reaction is proportional to the rate of the reactant collisions. The rate of the reaction is proportional to the rate of the reactant collisions. It's important to note that every collision does not lead to a reaction, right? Every collision does not lead to reaction. So even though the reactants are colliding with each other, every time that they collide, they don't necessarily form the product, right? So if we look into, well, how do they need to collide in order for it to lead to a reaction? And there's two things that must happen, right? One, the reactant molecules must be oriented properly when they collide, right? They must be oriented properly when they collide, and they must have enough kinetic energy to react and form products. So these 3 points is what's called our collision theory postulates, or the 3 things that must be true within collision theory for reactants to form products or for a reaction to take place. This adequate kinetic energy is what is called the activation energy. So it's the minimum energy necessary for the reactants to go over, essentially in forming a product. So I'm going to come back to that because we've seen activation energy in our reaction diagrams, but we hadn't explicitly named it. So we're going to come back to that. Here's an example. We have carbon monoxide and oxygen gas interacting with each other. So if the oxygen of the carbon monoxide, right, collides with the oxygen gas, this collision can happen, but it won't form a reaction, right? We actually need the carbon of the carbon monoxide to interact with the oxygen gas molecules in order to form carbon dioxide, right? So this is what we mean by the orientation must be right. So let's talk about a transition state model, which is really the same as what we've seen, right, in our reaction energy diagrams. So recall we have the potential energy plotted on the y-axis. On the x-axis, we just have our reaction path. You may see reaction coordinates, extent of a reaction, right, on the x-axis. And as we go from reactants to products, the reactants form what's called an activated complex. It's considered an intermediate. It's like the step or the stage that they have to go through before they form products. So the state of our overall system at this activated complex is called a transition state. So I'll mostly just use the term transition state when going from reactants to products, but just know that this intermediate that the reactants form is called an activated complex. And just intuitively think about that, right? It's an activated complex because the reactants have collided in such a way, right, where they've satisfied all 3 of those points under the collision theory to form a complex that's activated or ready to form the products. So let's look at this model, right? So we've previously seen this reaction diagram going from reactants A plus B to our product C plus D. And remember, the difference in the energy of the reactants and products is our enthalpy, or delta H. Now, this is the transition state. So as our reactants collide with enough kinetic energy, they will form this activated complex at this transition state. So E sub A, this is our activated energy. This is our activated energy. So they've collided with enough energy where they're basically able to overcome this energy barrier of whatever the activated energy is. They form this transition state, and then it's downhill from there in forming the products, right? In forming the products. So this is what our transition state model is, which is basically just our energy diagram, but we are specifically showing the transition state.